Welcome back. Let's look at examples of vector projection. All right, so here's our first example. We want to find the projection of vector v onto vector u and the vector component of v orthogonal to vector u. All right, and then vector v is equal to the position vector of the point 9, 7, and vector u is a position vector of the point 1, 3. All right, now in order to solve this problem, it's going to be helpful for us to draw a picture. And so let's say that this is vector v. All right, that's going to be vector v. And then let's say that this is vector u. All right, that's going to represent vector u. The projection of vector v onto vector u will be another vector. It will be the vector that starts at the same point as these other two vectors, but reaches out to an imaginary line from the terminal point of vector v that is perpendicular to vector u. All right, and so that vector will look like this. That vector is going to represent the projection of vector v onto vector u. It's the vector that vector v would make in the direction of vector u. So that's the projection, but what is the vector component of vector v orthogonal to vector u? What does that look like in this diagram? Well, first of all, it's important to note that this projection vector is also a vector component of vector v. It just has a special name of being the projection vector. But it's also the vector component of vector v that is parallel to vector u, right? This vector is parallel to vector u. It has the same direction. So the vector component of vector v orthogonal to vector u will be this vector right here. This is the vector component of vector v orthogonal or perpendicular to vector u. All right, and the reason we call these two vectors vector components of vector v is because if we were to add those two vectors together, they would be equal to vector v. All right, and so let's label them. I'm going to call our projection vector, vector w1, and then our other vector, the vector component of v orthogonal to u, this vector right here, I'm going to label with vector w2. Okay, and so vector v is equal to vector w1 plus vector w2. All right, so in this example, we want to figure out what these two vectors are. We want to know the vector component of vector v that is parallel to vector u. That's the projection of vector v onto u. And we want to know the vector component of vector v that is orthogonal to vector u. All right, that is this vector. And in order to find those two vector components, you need to know the following formulas. Vector w1, or the projection of vector v onto vector u, will be equal to the dot product of vector v and vector u divided by the magnitude of vector u squared times vector u. All right, and then once you have that vector, the projection of v onto u, you can use that to find vector w2, because vector w2 is equal to vector v minus vector w1, which is the same as vector v minus the projection of vector v onto vector u. All right, it's important to read this notation correctly. The subscripted vector is the vector being projected onto, right? We're projecting vector v onto vector u. That's what we want to find here. All right, and so it's important to notice in the actual formula for the projection of vector v onto vector u, that vector v only appears once in this formula. Everything else is related to vector u, the vector that we are projecting onto. Okay, recognizing that might help you remember this formula just a little bit better. But anyway, let's use this formula to find the projection of vector v onto vector u. We will have that vector w1, which is equal to the projection of vector v onto vector u. That will be equal to the dot product of vector v and vector u. And the dot product of two vectors is equal to the sum of the product of corresponding components. So we'll multiply the x components together and add that to multiplying the y components together. So we'll have 9 times 1, which is 9. So we'll have 9 plus 7 times 3, which is 21. And then that will be divided by the magnitude of vector u squared. And so let's do that. The magnitude of vector u will be the square root of the sum of its components squared. So we're going to be squaring the square root of 1 squared plus 3 squared. Right? The square root of the sum of the components squared, and then we're squaring that magnitude. And just a quick side note, I might do this for an example later in this video. You could take a little shortcut here. The magnitude of a vector squared is the same thing as the dot product of that vector with itself, right? Vector u multiplied by itself via the dot product is equal to its magnitude squared. That's one of the properties of the dot product. So you could just take the dot product of vector u with itself and do that in the denominator instead, and you would get the same answer. All right, so you would multiply 1 by itself and add that to multiplying 3 by itself, which, as you'll see, is exactly what we're going to find in the denominator here. But first, remember that this whole quantity is still multiplied by vector u, so I'll just write that in here. But then if we simplify, this will be equal to 9 plus 21, which is 30, so we'll have 30 divided by this quantity, but the square and the square root will cancel each other out, so we're just going to have 1 squared plus 3 squared, which will be 1 plus 9, which is 10. So we'll have 30 divided by 10 times vector u, and 30 divided by 10 is 3. So this is equal to 3 times vector u, but now I'm going to write in what vector u is equal to. So we'll have 3 times the vector of the point 1, 3. Okay, so now if we multiply 3 by both of these components, we will then have vector w1, or the projection of vector v onto vector u. So let's simplify. This will be equal to the position vector of the point 3, 9, because 3 times 1 is 3, and 3 times 3 is 9. Okay, so this vector right here represents the projection of vector v onto vector u. It's the vector that is made by vector v in the direction of vector u, okay? Or you could also call it the vector component of vector v that is parallel to vector u, or it's along vector u. Okay, so that's the projection of vector v onto vector u. Now let's find the vector component of v orthogonal to vector u, and that's going to be vector w2, right? That vector is orthogonal to vector u, and to find that, we need to subtract our projection vector from vector v. So that should be pretty simple. Let's work on that next. We will have that vector w2 is equal to vector v minus the projection of vector v onto vector u. And so that will be equal to the position vector of the point 9, 7 minus the position vector of the point 3, 9. And so if we perform this vector subtraction, we will subtract these components from these components. So we'll have 9 minus 3, which is 6. So we'll have 6, 7 minus 9, which is negative 2. And so the position vector of the point 6, negative 2 is the vector component of v orthogonal to vector u. That is vector w2. Okay, and so that's how you find those two vectors. And just like we said at the beginning, these two vectors are the vector components of vector v, so adding them together should give you vector v, which they do. 3 plus 6 is 9, and 9 plus negative 2 is 7. Okay? So these two vectors are the vector components of vector v, where one is parallel to vector u and the other is perpendicular to vector u. Let's take a look at another example. Okay, so next up we want to find the projection of vector x onto vector z and the vector component of vector x orthogonal to vector z. And vector x is equal to the position vector of the point 8, 2, 0, and vector z is the position vector of the point 2, 1, negative 1. All right, so this is exactly like our previous example, except now our two vectors that we're working with are in 3 dimensions. You can see that they have a third component, a z component, and so that just adds a little bit of extra work to our process here, but we're going to be using the same formulas nonetheless. All right, but first let's just draw a picture of what we're working with here. In this problem, we want to project vector x onto vector z. So let's just draw a little picture of what that could look like. I'll let this be vector x, and so I'll label that here, and then this will be vector z, and so I'll label that. All right, and by the way, these obviously are not very accurate drawings of what vector x and vector z would be in a 3D coordinate system. I'm just drawing a general diagram here, so that you can kind of visualize what we're trying to find here. All right, but now the projection of vector x onto vector z, that vector will look like this. We'll draw an imaginary line down from the terminal point of vector x that is perpendicular to vector z, and the projection of vector x onto vector z will be the vector that is parallel to vector z and reaches out to that line. All right, once again, I'm going to represent that with vector w1. All right, and you could also view that as the vector component of x parallel to vector z, but then the vector component of x orthogonal to z would be this vector right here, vector w2. It's perpendicular to vector z and reaches up to the terminal point of vector x. Okay, and so vector x will be equal to the addition of those two vector components, vector w1 and then vector w2. Okay, so those are the two vectors we're looking for in this problem. Let's start with the projection vector. That's vector w1. We are looking to find the projection of vector x onto vector z. So that will look like this. We'll have the projection of vector x onto vector z. The vector you are projecting onto is the subscript of the word projection, or I guess the abbreviation of the word projection. All right, you read this as the projection of vector x onto vector z. X is doing the projecting, z is being projected onto. Okay, and so to write out the formula for that, what we'll do is we'll take vector x and multiply it by vector z via the dot product. That's the first part. So we'll have vector x multiplied by vector z, and then the rest of the formula is all going to involve vector z, the vector that we are projecting onto. And that will look like this. We're going to divide by the magnitude of vector z squared, and then we're multiplying that whole quantity by vector z. Okay, that is the formula for projecting vector x onto vector z. And so now let's calculate it. We'll start by taking the dot product of vector x and vector z. That will be equal to the sum of the product of the corresponding components. So we'll multiply the x components together, add that to multiplying the y components together, and add that to multiplying the z components together. So we'll have 8 times 2, which is 16. So we'll have 16 plus 2 times 1, that's equal to 2. And then we'll add that to 0 times negative 1, which is 0. All right, then we will divide by the magnitude of vector z squared, but now I'm going to use the property of the dot product that I told you about in the previous example. Remember that if we multiply vector z by itself via the dot product, that is the same as taking the magnitude of that vector and squaring it. All right, they are equivalent. So we'll just take the dot product of vector z with itself, and that will give us the denominator. And all that means is that we're going to be multiplying each of these components by themselves and adding that together. So here's what we'll have. We'll have 2 times 2, which is 4, plus 1 times 1, which is 1, and then we'll have negative 1 times negative 1, which is also positive 1. And that whole quantity will be multiplied by vector z. Now if we simplify, this will be equal to 18 divided by 6 times vector z, right? 16 plus 2 is 18, plus 0 is still 18, and then 4 plus 1 is 5, plus 1 is 6. Now 18 divided by 6 is 3, so this just becomes 3 times vector z. And so now, to find our projection vector, we just have to replace vector z with what it's equal to, and then perform that scalar multiplication. So let me erase vector z here and write it like this. We'll have 2, 1, negative 1. That is our position vector, vector z. And now let's multiply 3 by each of these components, and we will have that this projection vector is the vector 6, 3, negative 3. Right? 3 times 2 is 6, 3 times 1 is 3, and 3 times the negative 1 is negative 3. Okay, so that's our projection vector, or vector w1. It is the projection of vector x onto vector z, this vector right here. You could also view it as the vector component of vector x parallel or along vector z. But now let's use this vector to find vector w2, or the vector component of vector x orthogonal to vector z. And so to find vector w2, what we need to do is take vector x and subtract vector w1, right? You take the vector that you are projecting onto the other vector and subtract the projection vector that you found, right? So we'll have vector x minus vector w1, or I'm just going to rewrite that to be our projection vector, which is the projection of vector x onto vector z. Okay, so here's what we'll have. This will be equal to vector x, which is the position vector of the point 8, 2, 0, and we'll be subtracting our projection vector, which we just found, and that is the vector 6, 3, negative 3. Okay, so now if we perform this vector subtraction, we'll subtract each of these components from their corresponding components in this vector. Here's what we'll have. We'll have 8 minus 6, which is 2. Then we'll have 2 minus 3, which is negative 1. And then we'll have 0 minus negative 3, which is the same as 0 plus 3. So we'll have positive 3. Okay, and so this vector right here is vector W2, or the vector component of vector x, orthogonal to vector z, which also means perpendicular. All right, that is this vector right here. It is the vector component of vector x, perpendicular to vector z. Okay, and so now we have completed this example. We found both our projection vector and the vector component of x, perpendicular to z. Let's take a look at another example. Okay, so next up we have for vector c equals 2i plus j plus 2k, and vector d equals 3j plus 4k, find the following. And we have two projection vectors that we want to find. We want to find the projection of vector d onto vector c, and the projection of vector c onto vector d. All right, it's important that you are able to read these notations. These two vectors are not the same. Switching the location of these two vectors in this notation completely changes the vector. Whichever vector is the subscript of projection is the vector that we are projecting onto. The vector that is not part of the subscript is the vector doing the projecting. All right, so let's draw a picture for these two projections so you can see the difference in the vectors that they represent. All right, so let's say that this is vector d, and I'll label it as such, that's vector d. And let's say that this is vector c. All right, so this is vector c. The projection of vector d onto vector c will be the vector that reaches out to the imaginary line drawn from the terminal point of vector d down to vector c, where that line is perpendicular to vector c. All right, so this is perpendicular, and our projection vector will be this vector right here. All right, that is this vector that we want to find. Now, in the case of the projection of vector c onto vector d, let's use the same diagram. The projection of vector c onto vector d is going to look a little bit different. It's not going to be the same vector. In order to draw the projection vector of vector c onto vector d, we need to draw an imaginary line from the terminal point of vector c that is perpendicular to vector d. But first, let's extend vector d with an imaginary line here, so that then we can see that the projection vector would reach out to right here. So the projection of vector c onto vector d would be represented by this vector. All right, that is the vector we are trying to find. It's a vector that's longer than vector d, but that doesn't matter. It is the projection of vector c onto vector d. Okay, so those are the two vectors that we are trying to find in each of these cases. Now, in order to calculate them, you need to make sure to set up the formulas properly. Because while the structure of the formula that we use to calculate these projection vectors is the same, the vectors we use in each part of the formula will be different. All right, and so here's what we'll have. The projection of vector d onto vector c will be calculated by first taking the dot product between vector d and vector c, and then dividing it by the magnitude of vector c squared, and then multiplying that whole value by vector c. All right, the easiest way to remember this formula is that the vector doing the projecting, vector d in this case, only shows up in the formula once. You multiply it by the other vector via the dot product, and then the other vector that you were projecting onto makes up the rest of the formula. You divide by its magnitude squared, and then multiply by that vector. All right, and so how does that differ from this projection vector? If you want, feel free to pause the video and see if you can write out the formula here first. But I'm going to go ahead and do it now. It's going to look like this. We'll have vector c multiplied by vector d via the dot product, and then we're going to divide by the magnitude of vector d squared, and then that will all be multiplied by vector d. Okay, vector c is doing the projecting this time. We're projecting onto vector d, so vector c is multiplied by vector d via the dot product, and then the rest of the formula is made up of vector d. We divide by the magnitude of vector d squared and multiply by that vector. Okay, so hopefully you can see the difference in these two formulas and the way they're set up, but now let's go ahead and actually solve for each of those projections. Let's start with the projection of vector D onto vector C. We have the dot product of D and C, which is equal to the sum of the product of corresponding components. Now in this case, our two vectors are given to us in standard unit vector notation, so the components of our vectors are going to be the coefficients of our standard unit vectors I, j, and k. The coefficients of I are the x components, the coefficients of j are the y components, and the coefficients of k are the z components. And so we'll multiply the x components, add that to multiplying the y components, and add that to multiplying the z components. All right, now in this case, vector D doesn't have an x component, it doesn't have an I term, so we can assume that the coefficient is 0. So first up, we'll have 2 times 0, that's equal to 0. Then we'll add that to 1, the coefficient of j, for this vector times 3. That's the coefficient of j here. So we have 1 times 3, which is 3, so we'll add that to 3, and then we'll add that to 2 times 4, the coefficients of k. And 2 times 4 is 8, okay? Then we'll divide by the magnitude of vector c squared, and you could calculate that the traditional way if you wanted to, but I'm going to use that trick that I showed you in the previous two examples, that the magnitude of a vector squared is the same as the dot product of that vector with itself. So I'm just going to perform the dot product of vector c with itself. And all that is multiplying each of the components by themselves and adding them together. So we'll have 2 times 2, which is 4. So we'll have 4 plus 1 times 1, which is 1. And then we'll add that to 2 times 2, which is 4. So we'll have 4. Okay? And then all of that is still multiplied by vector c. Now if we simplify, this will be equal to 0 plus 3, which is 3, plus 8, which is 11. So we'll have 11 divided by 4 plus 1, which is 5, plus 4, which is 9. So we have 11 ninths times c, but let's actually write in what c is equal to. We're multiplying by the vector 2i plus j plus 2k. All right, and so we want to multiply 11 ninths by each of those terms. And that will give us a final answer of a projection vector represented by 22 ninths times I plus 11 ninths times j plus 22 ninths times k, right? 11 times 2 is 22, so we have 22 ninths. 11 ninths times 1 is 11 ninths, and 11 ninths times 2, once again, is 22 ninths. All right, so that right there is the vector that represents the projection of vector D onto vector C. This vector right here. Okay, so that's this projection vector. We now found it. And by the way, you could write that using our other vector notation as well, the standard vector notation. It would look like this. You just take the coefficients of I, j, and k to make your vector. But anyway, let's work on finding this other projection vector. We'll start by calculating the dot product of vector c and vector d. Now technically we already did this. We did it up here for this projection calculation. The dot product is commutative, so vector d times vector c is the same as vector c times vector d. But now I did erase our work, although I remember that the result was 11, but I'll just go through the work again anyway, so that you can see that it's the same. So we'll multiply each of the components together for c and d. We'll have 2 times 0, right? We don't have an I term for vector d, so our x component is 0. So we have 2 times 0, which is 0. I'm not going to bother to write that. But then we have 1 times 3, which is 3. So we'll have 3 plus 2 times 4, which is 8. All right, then we'll divide by the magnitude of vector d squared, which I'm going to calculate by performing the dot product of vector d with itself. That's the little shortcut to doing this a little bit quicker. And so we just take each of the components of vector d, multiply them by themselves, and add them together. So 3 times 3 is 9, so we'll have 9 plus 4 times 4, which is 16. Note that we could also multiply 0 by itself and add it to this, but that doesn't really change anything. So we can just ignore the fact that our x component is 0. That doesn't really matter for this calculation. Okay, so now all of this is multiplied by vector d, and 3 plus 8 is 11, and 9 plus 16 is 25, so this is equal to 11 25ths times vector d. Okay, so now let's work on performing this scalar multiplication. If I replace vector d with what it's equal to, I'll try to fit it in here as best as I can. We have 3j plus 4k. We want to multiply this scalar by both of those components, or both of those terms, and we will have a vector of 33 25ths times j plus 44 25ths times k. All right, that is the vector that represents the projection of vector c onto vector d. Right, we had 11 times 3, which is 33, so 33 25ths is our y component, and then 11 times 4 is 44, so we have 44 25ths as our z component. And then once again, if you want to write this vector in the standard vector notation, it would look like this. You would have 0, 33 25ths, and then 44 25ths. Okay? Those are the x, y, and z components from this vector. But anyway, that is the vector that represents the projection of vector c onto vector d. And so as you can see, with these two vectors that we found here, the projection of vector d onto vector c is not the same as the projection of vector c onto vector d. They are two completely different vectors. So it's very important that you understand how to read this projection vector notation. The subscript vector is always the vector being projected onto. This is the projection of d onto c. This is the projection of c onto d. Okay, let's take a look at a different example. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the video and take a look at the next example. Okay, so next up we want to find the component of vector v in the direction of vector u if vector v is equal to the position vector of the point 1, 2, 3, and the angle between vector v and vector u is pi divided by 3 radians. All right, so this is a different example than what we've worked with so far, but if you watched my lesson on vector projections, then you might recognize what we want to find in this problem. But don't worry, if you didn't watch the lesson, I'm going to briefly explain it here. What we want to find in this example is the component of vector v in the direction of vector u, all right, given what vector v is equal to. What that is asking us to find is the magnitude of the vector that is the projection of vector v onto vector u, right? If I draw a picture here, let's say that this is vector v, and then let's say that this is vector u, so I'll represent that as vector u. The projection of vector v onto vector u would be this vector right here, right? That would be the projection of vector v onto vector u. But another way that we refer to that vector is the vector component of vector v in the same direction as vector u, right? So if this is the vector component of vector v in the same direction as vector u, then what would be just the component of vector v in the direction of vector u? This is the vector component. We want just the component. Well, that would be the magnitude of this vector, right? If this vector represents the component of vector v in this direction, then the magnitude of that vector will just straight up give us the scalar value associated with that component for vector v. Okay, so what we want to find here is the magnitude of that projection vector, but we actually have a special notation for this calculation. We call the magnitude of this projection vector the component projection of vector v onto vector u, and there's actually two different ways for us to calculate it. First of all, here's the notation I was referring to. This represents the component projection of vector v onto vector u. It's just the magnitude of our projection vector. And we have two different formulas for that. One for when we don't know the angle between our two vectors, and then one for when we do know the angle. That's the angle theta right here. And so which of these two formulas are going to apply to this scenario? And I should just mention this real quick. Obviously, you don't have to use these equations or these formulas. You could just calculate the projection vector and then calculate its magnitude. But more often than not, these two formulas are going to be more convenient. They're going to be quicker. Also, in the case of this example, we don't know what vector u is equal to. We're only given vector v, right? We don't know the components of vector u. So it's not going to be possible for us to use our projection formula anyway, because we would need to take the dot product of vector v and vector u, which isn't possible here. And maybe that just gave away which one of these formulas we want to use, right? Because in this formula, we have the dot product of vector v and vector u, which we can't do in this case. However, we are given the angle between vector v and vector u, so that's a pretty clear indication that we probably want to use this formula because it includes the angle between our two vectors. All right, this angle theta is pi divided by 3 radians. This angle right here, this angle theta between vector v and vector u, that is equal to pi divided by 3 radians. So we can pretty easily calculate the component of vector v in the direction of vector u. The component of vector v in the direction of vector u will be equal to the magnitude of vector v, which we can calculate pretty easily. That will be the square root of the sum of our components squared. So we'll have 1 squared plus 2 squared plus 3 squared. And then we're multiplying that by cosine of our angle between our two vectors, which is pi divided by 3. So we'll have cosine of pi divided by 3. Okay, so now if we simplify, this will be equal to the square root of 1 squared plus 2 squared plus 3 squared. 1 squared is 1, 2 squared is 4, and 3 squared is 9. So we have the square root of 1 plus 4 plus 9. And we're multiplying by cosine of pi divided by 3, which is equal to 1/2. So we'll have 1/2. All right. Now 1 plus 4 is 5, plus 9 is 14. So we have the square root of 14 times 1/2, which gives us a final answer of the square root of 14 divided by 2. And so that right there is the component of vector v in the direction of vector u. It is the magnitude of the vector that is the projection of vector v onto vector u. Okay, and if you want to know the approximate value of that magnitude, if you plug it into a calculator, it's approximately equal to 1.87 and some more decimals. Okay, so that's about the length of this projection vector. And so that's it for this example. Let's take a look at one more for this video. All right, so here's our last example. We want to find the component of vector A in the direction of vector B if vector A is equal to 7i minus 3j plus k, and vector B is equal to 2i minus k. Okay, so this is actually pretty similar to our previous example. We want to find the component of a vector in the direction of another vector. In this case, instead of vector v and vector u, we're working with vector A and vector B. Okay, so if we want to find the component of a vector in the direction of another vector, what we're actually looking for here is the magnitude of the projection of vector A onto vector B, right? So to draw a picture of our scenario here, if this is vector A, and I'll label it as such, and this is vector B, all right, that's vector B, then the component of A in the direction of B will be the magnitude of the projection of vector A onto vector B. So if I draw our projection vector, it will look something like this. That is the projection of vector A onto vector B. That represents the vector component of vector A in the same direction as vector B. So the magnitude of that vector will be just the component of A in the direction of B. It will tell you the component of this vector in this direction of vector B. Okay? And so if we want to find that component of A in the direction of B, we need to use one of the following two formulas. These are the same formulas I showed you in the previous example. Of course, we do need to apply them to vectors A and B, not vectors V and U. But the formulas still do apply. This formula is for when you don't know the angle between your vectors, and this formula is for when you do. Now, last time we did know the angle between our vectors, but this time we don't, right? All we're given are what vector A and B are equal to. So it's a pretty easy choice here. We know we don't want to use this second formula. We want to use this formula right here. So what we're actually trying to find here, of course, is the magnitude of the projection of vector A onto vector B, but that's going to be equal to the component of vector A onto vector B. Notice that the placement of our two vectors is the same between the projection and the component, all right? The location of those vectors in these notations needs to match. Okay, and if we want to find that component of A in the direction of B, we need to use this formula where we'll have vector A multiplied by vector B via the dot product, and then we will divide by the magnitude of vector B, right? When you have the component of V in the direction of U, you have V multiplied by U via the dot product, and then you divide by the magnitude of vector U. Notice that U was the vector in the subscript, or the vector that we were projecting onto, and so we followed that pattern for vector A and vector B, which means that we would have vector A multiplied by vector B, and then we would divide by the magnitude of vector B, okay? I hope that makes sense how we applied this formula for vector V and U to vector A and B. We just replaced V with A and U with B, okay? So now, let's actually calculate this component of A in the direction of B. Let's take the dot product of A and B. That will be equal to adding the product of the corresponding components between our vectors. So we'll start by multiplying the x components together. So we'll have 7 times 2. Those are the x components because they are the coefficients of I. And 7 times 2 is 14. So we'll have 14 plus the product of our y components. So we'll have -3, the coefficient of j, times 0, right? Vector b doesn't have a j term, so that means that the y component must be 0. So we have -3 times 0, which is 0. Then we'll add that to the product of our z components, which are 1 and -1, right? Those are the coefficients of k. And 1 times -1 is -1, okay? And then that will be divided by the magnitude of vector b, which is equal to the square root of the sum of the components squared. So we'll have the square root of 2 squared plus -1 squared. You could also add in 0 squared, since the y component is 0, but adding 0 to this isn't going to change the value. Anything plus 0 is just itself, okay? So now let's simplify. This will be equal to 14 plus 0, which is 14, plus -1, which will be 13, right? 14 minus 1 is 13. And then we are dividing by the square root of 2 squared plus -1 squared. 2 squared is 4, and -1 squared is 1. So we have 4 plus 1, which is 5. So we have the square root of 5 in the denominator. Okay, and so this would be our final answer. This is a perfectly fine way to represent it. But if you like to rationalize your answers, if you like to remove square roots from the denominator of your expressions, you could multiply this fraction by the square root of 5 divided by itself, and that would give you 13 square roots of 5 divided by 5. And then that square root is no longer in the denominator. Okay, the square root of 5 times 13 is 13 square roots of 5, and the square root of 5 times itself is 5. And so that right there is the component of A in the direction of B. It's the magnitude of the projection vector for the projection of vector A onto vector B. This describes the component of vector A in the direction of vector B. Okay, and once again, just like the previous example, if you want the approximate value of this answer, it's approximately equal to 5.81 and some more decimals. That is about how long this projection vector is. It's about 5.81 in length. All right, and so with that, that is it for this example, which was the last example for this video. But if you do want to see another example, I do have more available on my membership site, so feel free to look into becoming a member if that interests you. If you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now, so I will see you next time.